Houston. October, mid-October? Oh, really? Hmm. Yeah. Oh, really? Nice. Awesome. Yeah, that's like one of the. Oh, yeah. It's natural. It's just, yeah, so it's good. It's better for your systems just to be out in nature and relax. Yeah.
All right, it is the noon hour,
Yeah.
and we are recording. So it's kind of weird not having a 2-day work week, you know, last week. So I'm feeling that should be the norm, right? Just work 2 days. The reverse weekend, right? We get the 2 days of work and 5 days off. That was a horrible break, though. I was just worried I was going to get hit by a hurricane the whole time. All right, so I think I'll finish all of chapter 2 today. When we get to chapters 3 and 4, we'll slow down a bit more. And it's just because the stuff I'm thinking this stuff is relatively easy in terms of the material. I'd rather spend more time on the harder stuff. So today we're going to talk about atomic theory. And I remember one day I was, so at UH Minot on Fridays, different departments can have different drinking events. And I remember I attended one of these events, and there was an angry, drunk individual who told me, he says, "I don't believe in atoms. You're a chemist. I don't believe in atoms." And so I was like, well, you know, this is my opportunity to shine. If I can convince this person who says he doesn't believe in atoms that atoms do exist, then I'm going to be the best teacher ever. And after talking to him for a good 10 minutes, he said that he was just angry about pesticide use, that he actually does believe in atoms or something like that. But I did a mini lecture, which you'll see here, when I went over things like, oh, so here's Dalton's atomic theory, and this is why he thought they were atoms, and this is what that means. So we're going to go over this a little bit. Well, we're going to jump into it a little bit. But okay, so the atomic theory, and what's nice now is that, I mean, this is a pretty solid theory, right? There's not too many people except the occasional drunk person at UH Manoa is going to come up and say, like, I don't believe in atoms. You know, we all kind of, you know, atoms are pretty real because we can see them. Like, here is an image of atoms. So those little pimple-looking things are atoms. And when I say see with the imaginary quotation marks over it, so if you look at a wavelength of violet light, about 400 nanometers, about 800 hydrogen atoms can fit within that 400 nanometer, or 700 nanometer red light, about 1400 hydrogen atoms can fit in that. We can't see atoms with a microscope. So it doesn't matter how powerful a microscope, we won't be able to see them that way. But we can image them using a technique called scanning tunneling microscopy. So what that is, see this looks like a bunch of grapes there? That is a piece of tungsten, so like what they used to put in light bulbs. And you have a surface, you have a piece of tungsten, and you scan back and forth across a surface. And you put a huge potential, at least locally, across that tungsten, and you get a signal where there is an electron cloud. And if you look at this artist picture, you see that the atoms here, they look like tennis balls. They're even a little fuzzy. So the atoms there look like tennis balls. Here, they look like pimples. Why is that? Well, when you have a circular spherical atom there, you get a signal from the side of the tungsten as well. So the signal output, even though atoms are spherical, it looks more like kind of like that pimple sort of shape. That's just because of the nature of the fact that it's not a long single line of tungsten atoms. It's like a bunch of grapes, kind of like what it's shown here. So, and you can even do some art with that, or draw symbols with atoms there. So scanning tunneling microscopy. And atomic theory is basically that all matter, there's matter that's not made of atoms, so neutrinos, pions, muons. That's kind of above and beyond this course. But I mean, really matter that we really care about. I mean, in terms of contemporary society, we don't really sit around and think about, about pions or something like that. At least I don't. Some people might, but I mean, it doesn't have anything to do with what I'm touching in the desk right now, or what my iPad is made of. So, this is made of atoms. So, all matter, like I said, is made of atoms, and the idea is that these atoms then are exchanged in chemical reactions. So atomic theory is all matter, I should say atomic matter is made of atoms. And for instance, if you see a process here like sodium and chlorine, sodium element of sodium and chlorine element gas there, they're made of each type of atom, sodium atoms, chlorine atoms. And then a compound like sodium chloride table salt is just those atoms then mixed together. And a thing to note is that you have here 7.7 grams of sodium, 11.9 grams of chlorine will make 19.6 grams of chlorine. So this is also called the law of definite proportions. So that means that when a compound is formed, it is made with the specific amount of each element. So water, for instance, it's 1 to 9 for 1 part hydrogen in mass to 9 parts oxygen in mass will make 10 parts water. And if you have 2 parts hydrogen and 9 parts oxygen, you'll get 10 parts water plus 1 part hydrogen left over. So you cannot form any other type of material. That's called the law of definite proportions. So there we go. So Dalton's atomic theory, I wouldn't say he's the first one that came up with this idea. The ancient Greeks came up with this idea first. Of course, they only thought there were 4 elements, but they also thought atoms were hard and spherical. So Dalton just kind of, I don't know if he found that out from Greek, but he rediscovered it of sorts. It took these 3 laws: the law of conservation of mass, the fact that matter is neither created nor destroyed. And again, this is a law, so can laws be broken? Yes. When is the law of conservation of mass broken? In nuclear reactions by the relationship E equals mc squared. So under certain circumstances, matter and energy are interchangeable. So like the law of conservation of energy is another law, the breaking of that law is in nuclear reactions. But for chemical reactions, this more or less holds true. And I'm saying more or less because you could argue that when electrons give off when they get more bound, they do in fact lose some of their mass. But right now we have it's beyond our precision to measure them. But so law of conservation of mass, that means matter is neither created nor destroyed in a chemical or physical process. Law of definite proportions, like what this illustrates here, that only in these ratios will elements form specific compounds. And then the law of multiple proportions, that's when you have elements can form different compounds but in different ratios. So another one for hydrogen peroxide, so that would be 2 parts hydrogen to 32 parts, so it'd be 1 to 16 then. Okay, so that means that 1 part hydrogen to 16 parts oxygen will form 1 part, or will form the 18 parts, 17 parts peroxide. Sorry, I'm getting my math in my head wrong. So that's so 1 gram hydrogen, 16 grams oxygen will make 17 grams peroxide. And if you try to change that, you'll get excess in 1 if you do that. But then again, you look at water, it's 1 to 9 for that. So 1 part hydrogen and 9 parts oxygen will give you water. So you have 2 different compounds made from the same elements, but in different proportions. That's the law of multiple proportions. So what Dalton did is he took this, he says, well, you know what? All the elements, they have these really tiny units, and I'm going to call them atoms. And then these atoms, they're all the same. That's wrong. These atoms of the elements, they're all the same, and they're spherical. That's also wrong. Although he's right about them being kind of spherical, but he thought they were hard and you couldn't break them apart. That was wrong. So Dalton came along, and then there's some other things. So cathode ray came about. Cathode rays, you shoot, an old television set is known as a cathode ray, CRT, cathode ray tube. The old televisions worked by, you could have like a little filament and you would run current through, it would spit off electrons, and you put a plate around that, and you could shoot electrons down a tube, a vacuum tube, and that was the cathode ray. And you can bend the electrons with magnets, and then you could shoot them at different parts of a screen, and then you would get an image from those electrons shooting and then being bent in the screen. So that's how old televisions worked. And black and white TVs only had black or white. A color television had 3 colors, red, blue, and green. And they're little kind of hexagonal patterns. Now our televisions are typically pixelated, and they have liquid crystals in them. So, which is a different process. And we also got the charge to mass ratio of the electron here, and then the next big step was then, I mentioned this last class, was the plum pudding model of an atom. So Dalton said that atoms were hard and indestructible, but then we're like, wait, we can rip electrons off of atoms. So obviously atoms are not hard. So what we came up with instead was the idea, like I said, the plum pudding, like the blueberry muffin model, where you have a big muffin with lots of cake in it, and then blueberries stuck in it, and then those blueberries are like electrons in the big whole muffin. That's like this ball of positive charge, and that was what described the atoms. So although they're still not sure, this here, the plum pudding model, suggests that atoms are basically like, they're flimsy. There's nothing to them. Dalton said that they're hard and spherical. So then Rutherford came along. He says, you know what, I'm going to prove this. I'm going to say which one is which. Oh, here's the plum pudding model. All right, so here's the plum pudding model. He was saying, like, all right, if we have the plum pudding model being correct, I can shoot radiation. And this is how, the smoke detectors in this room here, they work off of lasers. If there's smoke that comes up, the smoke will cross the laser, and then without the laser hitting the detector, the smoke alarm will go off. Most people in their houses, in my house, for instance, I don't have a very expensive system. I've got the ones you buy, it has a battery in them, and you stick up on your ceiling. The way those work is similar to this. You have a source, an alpha source specifically. Alpha source in most smoke detectors is an element called americium. I don't know what Rutherford used. He probably used uranium or something like that. So there's a radioactive source, but the same thing with our smoke detectors. We have americium, an alpha source, and it shoots radiation. Okay, and then we have a detector not in the path of the ionizing radiation, and if smoke crosses the beam of ionizing radiation, it will ionize the smoke, or steam if you have a real sensitive one, you just take a hot shower. And then a detector that will detect charged particles, and then if it detects charged particles, it will alarm. So same technology as our cheap smoke detectors here, but what Rutherford did is he took a piece of gold foil. So gold is an interesting substance. You can hammer it really thin. Like, if you've ever seen gold leaf, it's really, really thin. So you can take little pieces of gold and you can hammer it. You hammer it long enough, you can get a really, really thin piece of gold. He did that, and with this thin piece of gold, because gold is an element, it should be made of atoms. And from these he goes, like, all right, so if the plum pudding model is correct, oh, and behind it he put a screen, and now we use this, so phosphor, there's other things, cesium iodide will do this. I don't know what he used in his screen, but if radiation hits it, it flashes. So, and this is in the 19th century, so he gave his grad student a clicker. You ever go to a club or a bar and someone's like, you walk in and someone like clicks, another person walks in, you click. he gave his graduate student a clicker and put him in a dark room and told him, like, all right, I want you to go behind here, and I want you to move around this, and I want you to press click every time you see a flash of light, and do that for like an hour or something like that, and just move, step here and do that for an hour, and do a step here, and the graduate student, he did this for about 2 weeks, and then he took the data, compiled it off, and gave it to Rutherford, and Rutherford was like, this is wrong, do it again. So the graduate student then did this for another 2 weeks, and then compiled the data. I don't know who the graduate student was, but this is the story supposedly. And then the graduate student gave Rutherford again the data, and he says, no, this is still wrong, do it again. The graduate says, hey, listen, Rutherford, Professor Rutherford, you've been doing professorly things in your tweed jacket, smoking your pipe, drinking coffee. I've been here in the dark doing this for weeks. Like, it's the way it is. If not, you do it yourself. So Rutherford is like, that must be right. And he thought about what went on. And what he found out was, so what was the controversy is, most of the radiation went straight through the piece of gold. But some was deflected. It was deflected off all different angles. Even some of it seemed to go back at the source. So he goes, what's going on here? And what he came up with the idea was the idea of a nuclear atom. So where the negative electrons on the outside, they're very not massive, but most of the mass is in the center of the atom. So then most of if you're hitting something like a really high energy beam of radiation, most of it's just going to fly right through the atom. But if both this really concentrated mass in the center, you will occasionally get deflections. And he was right about that. So, and specifically, the protons and neutrons have about 2,000 times as much mass as an electron. So electrons' mass is 1/2000-ish of the atom, and the rest belongs to the nucleus. So most of the matter of the atom is centered right there at the nucleus. So this is similar to our current model of the atom, and that's the quantum mechanical model. So much of what we talk about today we will cover much more in depth in chapters 7 and 8. 7 deals with the quantum mechanical model. Chapter 8 deals with periodic trends. So we're going to talk about the elements, though. The number of protons, so what defines an element is the number of protons. If an atom has 6 protons, it's an atom of carbon. If an atom has 26 protons, it's an atom of iron, for instance. So the number of protons defines the element, and you sometimes see, this is more in when things are in nuclear terms. The bottom number is known as the atomic number, and that's the number of protons. The top number is the mass number. That's the number of protons plus the number of neutrons. And the mass, for these we assume then that the mass is of a proton and neutron is about what's known as an AMU, atomic mass unit. An atomic mass unit is based off of 12 grams of carbon-12. So atomic mass unit is based off of carbon-12. And like I told you, Rutherford was wrong, and because for an element, you can have, for an atom I should say, you can have an atom that has different number of neutrons. Same number of protons, so different number of neutrons. And does anybody like the show The Simpsons? I like The Simpsons. What's the name of the baseball team? Yep, Isotopes. Right? Why? Because the nuclear power plant. So it's isotopes or something nuclear, or nuclear, if you're from Texas. So number of protons. Carbon is defined by having 6 protons. So, and here are 3 common isotopes of carbon. And so since it's carbon will always have 6 protons. Question?
Can you clear that off the screen?
Oh, geez. Thank you for letting me know. I didn't see that. I hate that about Skype. Ever since Microsoft took over Skype, I hate those updates. Yeah, thanks for letting me know there. Okay, another definition of an atom, atoms are neutral. So the number of protons equals the number of electrons. So I always feel so evil doing this. Now the mass number at the top, so this 12 here, that's the number of protons plus the number of neutrons. So that means for carbon 12, we have 12 minus 6, or 6 neutrons. And then for carbon 13, we have 13 minus 6, or 7 neutrons. And carbon 14, we have 14 minus 6, or 8 neutrons. So are you seeing how I'm calculating the number of protons? Well, protons, another way to look at it is the periodic table. So carbon here, atomic number, if you can read that, I don't know how good your vision is in the small screen. It says atomic number 6. And then above that, in the pink square, you have C above that says 6. So that's the atomic number, that's the number of protons. So, does everybody see where this is coming from? Good question.
Can you just repeat that again one more time?
Can I say what?
Can you just repeat that again one more time?
Okay. Which part?
Like the atomic number and then your protons.
Okay. The atomic number. I don't know if I can zoom in on. The thing is, I can only see here. I have a periodic table somewhere else. Okay, here we go. Okay, but that's fuzzy. Shoot. Do I have? Okay. Do you see there that says chlorine? And you see this number 17? That's the atomic number for chlorine. That means that chlorine has 17 protons. Okay, and I'm going kind of like going back up to carbon. Carbon here, I can't zoom on this. There's a different app. But if you can see this, carbon here has 6 above it. That means, so hydrogen is 1, that means it's 1 proton. Helium is 2 protons, and all on. So gold here has 79 protons. That means if an atom has 79 protons, it's gold. So carbon always has 6 protons. Carbon always has 6. And then the top number, so for a specific nucleotide, so a specific atom, the bottom number is the atomic number, the top number is the mass number, is the number of protons plus the number of neutrons. So here carbon has 3 common isotopes. So here carbon 12, so carbon 12, since the top number 12 means protons plus neutrons, and carbon always has 6. So 12 minus 6 means 6, so 6 neutrons. And carbon 13 means it has an extra neutron. Carbon 14 means it has an extra 2 neutrons from carbon 12. Is that making more sense? Okay. All right, and since atoms are electrically neutral, they always have the same number of protons as the number of electrons. Okay, so this is my chance to see if you understand what's going on. So depleted uranium, uranium-238, has how many neutrons? So think about it for a second, and then I'm going to ask you. How many people think it's A, 238? How many think B, 92? How many think C, 146? How many think D, 350? So we're all over the board here, huh? Number of neutrons, so 238, uranium, 92. This is the atomic number. This is the number of protons. Okay, and then this is the mass number. This is the number of protons plus the number of neutrons. So how do we get the number of neutrons?
Subtract.
Yeah, it's 238 minus 92. And it's going to be that one there. Does that make sense? Does anybody have any other questions with this? Okay. So here is the periodic table. And a couple things to note about it. You're like, most students, when they see this, like, it's kind of a funny shape. It's probably what most people say. Like, it's a funny shape. What's going on with this garbage down here? And why is there a step ladder here? So that's usually the first two things that people say, besides that's a funny shape and then what's going on here. So how the periodic table should look, it should look something on the order like this. That's the way it should look. Because this part goes here. Okay, so why do we have the periodic table be this way and not written this way? Because if we do it as written on this sheet of paper, it can fit on a sheet of paper really well, and pieces of paper are close to the golden mean, and we think the golden mean is pretty. Okay, that's the reason why we do it this way, because it looks pretty. So why is there this step ladder? What does this step ladder here mean? That means that everything to the left here, including this, these are known as metals, and then over here to the right, these are nonmetals. Okay, so what's the difference between a metal and a nonmetal? Well, my Apple Pencil here is made of plastic, mostly, at least on the outside. And let's say, for instance, this whiteboard had 10,000 volts on it, and since plastic is mostly carbon and hydrogen, which are both nonmetals, what would happen if I touch here with 10,000 volts? Absolutely nothing. Here is my brass key, made of copper and zinc, both metals. What would happen if I touch a 10,000 potential with this? I'd be getting a shock. I'd be throwing my keys across the room. So generally speaking, mind you, generally speaking, metals conduct electricity well. Non-metals are insulators to electricity and to heat too. So metals tend to be conductors. Non-metals tend to be insulators. Other things, and again, these are general trends. So what would happen if I took this key and I took a hammer and whacked it? It would bend, right? What would happen to my Apple Pencil if I took a hammer and just whacked it? It would shatter, right? So nonmetals tend to be brittle, and metals tend to be ductile. Ductile means bendy, right? So kind of like if you look at a car, I've got a Honda Accord, that's what I drive. And if I get into a car accident, I get a fender bender. So something like a Corvette has fiberglass on the outside. If that gets into a car accident, they shatter. So that's the difference. So does that mean that all nonmetals do not conduct electricity? No. Carbon, graphite carbon, conducts electricity. DNA molecule conducts electricity. Diamond does not conduct electricity, but it conducts heat extremely well. It's one of the highest thermal conductivity materials. So these are general rules, so they don't fit all the time. Also with metals, so if you look, where's my Theodore Gray? I thought it was this page. Is it this page? Oh, there it is. Okay. So this is an app from Theodore Gray. If you look at the periodic table in the back of the classroom, it's the same one there. He wrote a book and he turned it into an app. It's actually kind of fun. But it costs about $15, so I do it because I'm a chemistry nerd. Right, so you can take this, here's gold for instance, and you can flip it around, and then you can see what gold is used for. So kind of thing. So if you notice something, a couple things to note. All of the metals, so left of that step ladder, they all look kind of the same. So here is molybdenum. So that's what molybdenum looks like. And here are some molybdenum or moly. So Sometimes you hear it called moly. There's moly nuts there. And then here's platinum. Do you have a solid hunk of platinum here? There we go. So do you notice that they look pretty much all the metals look very similarly. They're all kind of silver colored. Couple exceptions. Copper is reddish colored. Gold is yellowish colored. Osmium is a bluish sort of color to it. So you see here, there's kind of a bluish tint. It's hard to see in that one. A little easier to see here, I guess. Osmium has a bluish color to it. And potassium kind of has a purplish color to it. The purple color comes from the oxide, not necessarily the potassium itself. So same thing with the osmium. Osmium, the oxide, has a bluish tint. But, basically, all the metals look silver. So nonmetals, on the other hand, they're not really any consistency with this. So sulfur, not surprisingly, looks yellow. Right, and bromine looks kind of orange colored. Iodine looks violet or dark purplish color. But then you get these ones like right here. So this is silicon. That's a bad picture. Oh, maybe right here. Silicon is actually really shiny. Here's silicon. So this is silicon right here. It looks like a metal, right? But if you ever touch it, I don't know if we have it here, I haven't looked. If you touch it, it feels a little different than a metal. It looks shiny. It doesn't feel very bendy because it's not. It's pretty brittle. But silicon does not conduct electricity. So if you at least just sitting there. But if you put a potential of 5 volts behind it, it will conduct electricity. So that is essentially the basis of our computer systems right there. So we use silicon and the fact that the band gap, meaning the amount of energy it takes to conduct. So we humans, we're considered insulators. Our threshold is supposedly 60 volts. So meaning I don't conduct electricity, but if you put a wire and then 60 volts behind me, I will become, well, we're insulators. We get hot. Like electricity doesn't flow through us very well, but potential of 60 volts, then humans can conduct. Piece of iron just conducts. Doesn't matter. It conducts at 0 volts. Silicon needs 5 volts. So humans, we're mostly nonmetals. We're insulators. Metal like iron, like zinc, copper needs just conducts, doesn't need to have any potential behind it. Then your silicon has a band gap between conduction and valence band. We haven't talked about that yet, where the electrons lie. It's called a semiconductor. So it's referred to as a semiconductor or metalloid, sort of metal, right? So metal-ish, so metalloid. So there are certain elements that are not necessarily metals or non-metals. They're kind of both. We call them metalloids, like boron. Look at that, it's kind of shiny. It's kind of like a metal, but it's not. It doesn't conduct. Unless, I don't know what the band gap is for boron. Germanium here also looks kind of metallic, but it doesn't. So that's what that step ladder means. It discerns between the metals and the non-metals. And then the ones that lie along it tend to have properties of both. But not always. Aluminum, see underneath boron is aluminum, Al. Aluminum is definitely a metal. Okay, so it doesn't act like a non-metal. Although aluminum oxide does, which is kind of weird. So, and much of what I'm talking about, so these are general rules. So chemistry is an observational science. So this is things that we've observed, and then we've kind of tried to put general trends to it. So that's one of the reasons why people hate learning chemistry, at least that are not chemists. Because I'll mention rules, then I'll mention exceptions to the rules, and then there'll be an exception to the exception, maybe another exception under this case. So And this is not because I want to make your life difficult. It's because this is just how we've made sense to it. So all these rules. Okay. So this next question here. So metal, metalloid, dysprosium. And I will mention dysprosium. It's right there. Is dysprosium, how many people think it's a metal? How many think it's a non-metal? How many think it's a metalloid? So we've got half the class saying it's a metal and the other half not wanting to play. Dysprosium is a metal. And certain names, we give certain names in you. I'm going to say these so often, you don't have to worry about it. We give certain metals, certain groups of metals, certain names. We call this first column, we call these alkalis. Those are known as the alkalis. So maybe you've heard of an alkaline battery before. Alkaline means basic, means the opposite of acidic. So acidic and basic means alkaline. Alkaline batteries are basic batteries. And many of these terms come from the alchemists. So the alchemists, they were a group of people that believed, Newton was an alchemist, for instance. They believed that if you were pure of heart, you could do certain religious ceremonies or experiments. And from that, you could generate what's called the philosopher's stone. And from that, you could turn lead into gold and also make the elixir of life, which would give you eternal life. And maybe you're familiar with Harry Potter and the Sorcerer's Stone. They only call it the Sorcerer's Stone in the American version. The rest of the world got the Philosopher's Stone because that's the proper term. So many of these elements, names come from alchemists. There is no sort of any convention. Well, now we have the IPCC, which is located in Columbus, Ohio. They determine the names for everything now, but a lot of names came from previous things, like I know potassium, for instance, was discovered in Arabia. So from potash, because potash is if you burn, if you take ashes and you mix them in a pot of water, you can form what's called potash. It's potassium carbonate. You can use it to make soap. Okay, so potassium comes from that. Sodium comes from natrium. So if you wonder why is it sodium Na, it's from natrium. And iron, I mean, like and also across languages. I mean, ferrum is the Latin name. We call it iron. It's var in Hungarian. Okay, so it's different languages have different things, but in Hungarian, sodium is natrium. So and like copper, silver, gold. I don't know about copper, but plato is silver in Spanish. It's argentum in Latin. Gold is aurum in Latin. It's oro in Spanish. It's gold in English. I guess Spanish and Latin are kind of close for gold, but not for silver. I mean, so different languages, it's just different things. And gold is jing in Chinese, or Mandarin, I should say. So, I mean, what's kind of nice though, like you can kind of figure out. For a while when I lived in Hungary, I thought var for iron, I thought it was vanadium. You know. So, and tungsten. Where's tungsten? It's W. Oh, did I cover it up? Oh, it's right there. It's under metals. Tungsten. That was from German. It's Wolfram in German. So I mean, we have a hodgepodge of things there. A potpourri, I should probably a better word. Potpourri. But the alchemist did kind of make a standard set for it. So the first column are alkalis, and it means basic. So if you throw these metals into water, they form bases. Okay? And these metals right next to it, these are the alkaline earths. So if you throw them in water, they form bases as well. But where the alkaline metals are extremely soluble, the alkaline earths are less soluble, which means if you mix them with other things, they form precipitates, which means that stuff falls down to the bottom. So the alchemists were thinking earth, wind, fire, water, the elements. So you have an alkaline metal, but you put it in water, you get earth, you get solid coming out of it, so it's an alkaline earth. So that's where that term came from. Then this column here, this is called the halogens. That's Greek for salt forming. And then you have the noble gases on the far right. And noble used to be inert gases, but then we found out they react. So now we call them noble, which means they tend not to react. And the idea is noble, the nobility. It was like this is kind of a British thing. Like the commoners are considered to be very rambunctious, and the nobility is very stoic. So like I'm the queen or I'm the king. I gotta be careful of saying I'm the queen on YouTube. I'm royalty, and I'm having the happiest day of my life. Yesterday I had the saddest day of my life, and I'm exactly the same. I'm noble. So the idea of noble metals, they don't react. So I can write here halogen. And you will hear me say it so many times, you will be sick of it. Okay. And okay, now we're going to talk about something else. Ions. So atoms are neutrally charged, and in general, things bond to be like noble gases. So, and it's the electronic structure. So the numbers 2, 10, 18, 56, 54, 86, and 118. Those number of electrons, and those are the atomic numbers of the noble gases. Things bond, they tend to bond to go towards those because they are relatively low energy. So, and things go for low energy because of entropy, which we'll talk about in second semester. Things like being low energy. So right now you're sitting down. I know I'm standing up, but has anybody requested, like, can I do push-ups for the entire class? Is that okay? If I'm going to sit here I don't want to sit for an hour and 15 minutes. I want to do something really active. I want to do jumping jacks. No one's going to say that, right? So if you have to do something for the next hour and 15 minutes, you're going to pick a state that's low energy. Electrons are the same way. They want to be low energy. So they pick the lowest energy, and then they'll bond to be low energy. And those numbers just happen to be low energy. And why do they happen to be that way? If we did the quantum mechanics and all the math calculations, we would find out to be true. There are other bonding schemes, especially in the transition metals. Oh, I didn't talk about the middle. We call the middles here, we call them transition metals. And then we call this top line here, we call them rare earths. So if you ever heard of rare earth elements, and they're really important for computers and electronics, the rare earths are there. They're actually not that rare, but there are bonding schemes that work differently for them. They can for those. So it's not all just noble gas. For this class, it is all just noble gas. Okay, so atoms will bond to get to the electronic configuration of a noble gas, generally speaking. And what moves around, though, are the electrons. So the protons don't move. Remember, if you change the number of protons in an element, it changes the element. So carbon can become a positive ion by ripping off an electron. So carbon starts with 6 electrons. If you rip off an electron, that's 5 electrons, and now it has a +1 charge. If you add a proton to carbon, well, carbon's got a +1 charge, it must have an extra proton. If you add a proton to carbon, it becomes nitrogen, a new element. So positive ions lose electrons. That is known as a cation. And if you forget that, the T is like a plus sign. Okay, and negative ions gain electrons. Negative ions are known as anions. So let's see if you can figure this out. So uranium-238 +6. How many electrons does +6 ion of uranium-238 have? How many people think it's 146? How many think it's 92? How many think it's 98? How many think it's 86? Okay, good. People are going for 86. That's correct. If you're wondering, it's 92. 92 is the number of protons. That means it has 92 electrons. Plus 6 means 6 are removed. How about oxygen -2? How many electrons here? How many of you think oxygen -2 has 8 electrons? How many of you think 10? All right, everyone's going for that. Good. You get it. Moving on. All right, and what about us humans? What are we made of? And there's a whole field in this. It's called astrobiology. Astrobiology, trying to understand how life is originated, how life could exist outside of the Earth. And they are looking for, sometimes you'll see, looking for CHON. So CHON being carbon, hydrogen, oxygen, nitrogen. Why they say CHON? Because it kind of forms a word, right? The order would be HCON, but that doesn't really say anything in English. So CHON is something you kind of say quickly. So we are living creatures. What are we made of? If you look at by mass, humans, we are about 65% oxygen, 18% carbon, 10% hydrogen, and 3% nitrogen. And then a trace amounts of others. Most specifically, the most important one there is probably iron. But we have other elements. We have magnesium in our bones. We have zinc, these kind of things. A lot of elements in this. But then you look at by mass or by number of atoms. So notice that we are, by mass, we're mostly oxygen. By number of atoms, we're mostly hydrogen. But in carbon, we're not really that much, but we're called carbon-based life form. So maybe you've heard this before. What do they tell people? That you are at least 50% by mass of what? People say water. Yeah, that's partially true, partially not, because we have a lot of water in us. Our blood and our cells, so within the cytoplasm of our cells, and we're made of cells. Outside of our cells, we have like plasma and whatnot in our blood. We have lots of water in this. But we also have oxygen and hydrogen bound up in other things. We're called carbon-based because carbon as an element, and it's the only element that does this, it makes chains. Okay, so if you throw I used to do research with carbon, and I did a high vacuum situation. If you throw 50 atoms of carbon in a vacuum chamber and blast it with electricity, it'll form chains, long chains of carbon, just straight chains. If you throw 50 atoms of any other element, silicon, for instance, 50 atoms of silicon forms kind of like a cage, it's like a big ball. So silicon, up to 19 atoms, it forms kind of football-shaped clusters, and after 19 atoms, it'll form, we call them cage-shaped, kind of just more spherical. So people say like, oh, you can have life that are silicon-based. It wouldn't be life as we know it. So lots of the structures that are in biomolecules, like a cell membrane is a phospholipid bilayer. That means that there is a chain of carbon is the backbone of that, and it's about 23 to 25-ish carbon atoms long. So if you did that with silicon, it would be a clump. It wouldn't form a chain. So lots of biomolecules like DNA and other nucleic acids, they are chains. And if you put another element like silicon or germanium in there, it would just be clumps. They wouldn't form it. So life as we know, like I said, life as we know it really needs carbon. That's why we're called carbon-based, even though we're mostly oxygen or hydrogen or water of sorts, if you look at it that way. Okay. Now, changing topics yet again. So if you look at the periodic table, and let me pull up the periodic table again. If you can see some of these, hydrogen, it's underneath it, it's 1.0079. So you're like, well, that's close to 1. That's kind of cool. Helium is about 4. Like, okay. I can buy that. Lithium, it's 6.9. That's close to 7. I'm okay with that. And then you get to something like copper, and that's 63.54. Like, wait a second. Protons and neutrons, you can't have a half of a neutron. That's the thing with chemistry. You have to use something called discrete mathematics. You can't have a half an atom. You can't have half a proton. It has to be whole numbers. So what do these bottom numbers mean on the periodic table? So chlorine, for instance, is 35.45. So chlorine, for instance, is 75% chlorine 35, and it's about 25% chlorine 37. So chlorine, and this is, I don't know what the exact number is off the top of my head, but it's a 3-to-1 ratio, thereabouts. So what we've done in the periodic table is we've taken the terrestrial average, terrestrial meaning here on Earth. So if you look at the terrestrial average of the isotopes of each element here on Earth, it is more or less the same. There are a few exceptions where they are not the same, but this is generally held true, that the isotopic ratios for the different elements here on Earth are about the same. So, and even when they are different, the differences are not that much. So, for instance, there is basically no radioactive carbon-14 in fossil fuels. So, although the term fossil fuel is probably outdated. So, but meaning that it didn't come either. Well, it's more likely it didn't come from living things, but it's been dead enough a long time that all the radioactive carbon has disappeared. So, okay, so then the atomic mass, it is the weighted average of each isotope. So again, this is the sum, the sigma. The atomic mass equals the sum of the fraction of one isotope times the mass of that isotope. Let me illustrate that with this example. Copper has 2 isotopes, copper 63 with that mass and that abundance, and copper 65 with that mass and that abundance. What is the atomic mass of copper? And the atomic mass of copper, so that means we have to apply that equation up there. So then we have the fraction of isotope 1. So 69%, this is 0.6917. That's the fraction of that percent times the mass, 62.9396 atomic mass units, plus 0.3083 times the next one here, 64.9278. So you sum those up together, and you get 63.5525. And how many sig figs do we have? We have 4. So 4 sig figs there from the percents. So the mass then of copper, or the atomic mass of copper is 63.55. And if you can verify that here, it is in fact 63.55, or 546. But 5.5 to 2 sig figs. So that's someone's job, is actually to go through and make sure that this stuff is all the right amount. So that was I guess we don't do it that much anymore, but that was someone's job for a while, to make sure that all the atomic masses are the proper atomic masses for the periodic table. Hasn't changed that much since 1960. We've already done all that work. But does this make sense here? You take the again, this is a terrestrial average here on Earth, which means that if you go somewhere else, it could be different. And have you ever seen things like, oh, this meteorite came from Mars? How do we know this meteorite came from Mars? Because the isotopes are different. So that's the thing you have to note. With the periodic table, these elements here, a hydrogen atom here on Earth is the same as a hydrogen atom in the sun. Same on Mars, same as Alpha Centauri, one of our closest stars. It's the same as a hydrogen atom in the Andromeda galaxy, as is an atom of gold. So it doesn't matter when it was created in terms of distance from the Big Bang or time after the Big Bang and where it is. Each atom is the same, at least each nucleotide in terms of its structure. And its atomic spectrum is going to be the same. So that means an atom of gold on the moon is the same as an atom of gold here on Earth. But what can be different is the fraction of the isotopes. And they've looked at this for meteorites and moon rocks and stuff. So the moon has some Earth-like properties. It has some non-Earth-like properties. Or we've looked at the moon rocks that the astronauts have taken back and come up with the idea where the moon came from now. Do you know about where the moon came from? Have you heard that theory? Some people said yes and no. We think it came from a collision of the Earth with another Mercury-sized planet, and then there was a collision and it broke off that it vaporized basically the surface of both of us, and then the Earth congealed. Well, I mean the Earth was still a planet at that point in time. The moon, though, however, it shot off a bunch of debris and then by gravity formed the moon, and then it was also molten, and then it solidified, and that's why the moon is always tidally locked to us, right? We have a dark side of the moon because it's tidally locked with the Earth, and the gravity it moved closer. The molten part moved closer to the Earth. That's a different class. So, all right. Again, I'm sorry. How are we doing some more questions? Changing topics. Yet again, the mole. So we have a mole of something. So sometimes referred to as the chemist's dozen. So right, no, we use certain things colloquially. So I mean, I back in my fraternity days, we would talk about parties by the amount of beer that we bought. Like, if it was a 10 case of beer party, it wasn't that big of a party, but it was like a 50 case party. Ooh, right? And a case means 24, right? So if I say 10 cases of beer, you're like, you can probably picture 10 cases of beer stacked up or something like that. At least I can in my mind. I don't think I can convert it, so 10 times 24, that's 240. I was like, we had 240 cans of beer at this party, right? You know, we didn't do that. We take things and we apply another term to it, like pencils. So I know this now as a teacher, when you order pencils, they come in grosses and half grosses, or paper reams of paper, or even the boxes, right? I might go to the department secretary and say, I need 2 cases of paper. She understands exactly what I mean, right? I think is it 10 reams in a case or something like that? I don't say, I need 2,500 sheets of paper. She would probably tell me, how many boxes is that? You know, they're like, all right, I need 2. You know, kind of thing. I'm just making these numbers up. I don't know. What's that?
I said, you know how much a case of beer is?
I do. I have that. That's ingrained in my mind. Yeah, my pleasure center in my brain still remembers that. Okay, so we've come up with this term, though, called the mole. And this is also Avogadro's number. And Avogadro's number is 6.02 times 10 to the 23rd. And this is based off of carbon-12. So 12 grams of carbon-12 has exactly a mole, is a mole. So that's our definition of mole. And it is, at least, I know it's down to 6.022. I don't know beyond that. Somewhere I could look it up really, really big. The mole may change. Like I said, it may change to silicon within a decade or so. You know, but right now it's still carbon-12. And 602 times 10 to the 23rd, it's this many zeros. So hopefully you come up with two ideas. The first you think is, that's a huge number. That is a huge number. The other thing you think is, oh, atoms are really tiny. Yes, atoms are really tiny. That's why we need such a big number to deal with them. So that is Avogadro's number right there. There are other types of moles. There's a kilogram mole and a pound mole, which we may talk about later. But most of the time when people say mole, they mean gram mole. And if you say mole, you mean gram mole. So from this, we can do this to do certain problems. So for instance, how many copper atoms are there in 2.45 moles of copper? So before I get there, how many seconds in a year? Does anybody know how many seconds there are in a year? No one. Okay. But we can calculate it, right? We can start with 1 year, and we can multiply how many days in the year. I know it's quarter-ish. I know, but there are 365 days in a year, and then there are 24 hours in a day, and then there are 60 minutes in an hour, and there are 60 seconds in a minute. So have you noticed something here? The years can cancel, the days cancel, the hours cancel, and the minutes cancel. And from that, I can get the number of seconds. It's 365 times 24 times 60 squared. You don't have to tell me what it is. But this is called dimensional analysis. And we're going to do this quite a bit for the next 3 chapters and beyond. So what we've done here, we've just multiplied one number by 1 a bunch of times. 365 days is a year. We're multiplying by 1. 24 hours in a day, at least it was true in 1980, it's a little longer now. So days are getting longer. It was true in 1980, the 24-hour day. This is by 1. 60 minutes is being an hour. That's still true. That's a definition, right? From the Babylonians, actually. They came up with the 60 base for things. Same thing with the seconds in a minute. Good old Babylon. So we just multiplied by 1 quite a bit. So in this problem here, we're going to multiply by 1. Calculate the number of copper atoms in 2.45 moles of copper. So how do we do this? So 2.45 moles of copper. And I'd like to do boxes for 2 reasons. Number one, it's neat and easy. The other thing is I was an engineer for undergrad and made engineering paper. So I like the boxes that way. Okay, moles of copper. And then there are 6.02 copper atoms per mole of copper. Oh, I'm sorry, times 10 to the 23rd. Times 10 to the 23rd. Okay, so, think of a mole kind of like a dozen. And with the units, I'm being very explicit here with my units. A dozen doesn't really apply to anything specific. So the word dozen just means 12, right? It doesn't matter if I'm talking about beers, if I'm talking about reams of paper, or if I'm talking about shoelaces, right? So dozen is 12 of whatever I assign it to. So like a mole, I can assign it to copper atoms, hydrogen atoms. I can assign it to droplets of water. A mole of droplets of water is equal to about the ocean. A mole of baseballs is equal to the mass of the Earth-ish, thereabouts, kind of thing. So, and from this, the moles cancel, and I couldn't figure out how to erase these, so I have my calculator already pre-spitting out images. I just copy that with white paper or whatever, white electronic ink. And the answer then is, doing this on the 663, 1.47 times 10 to the 24 copper atoms. And notice something here with the calculator. When I put this in my calculator, I use this. It's this EE button on the calculator. Be careful. Do not use the E button. So don't use the E button. This EE button means times 10 to the whatever. So the E button means it's Euler's number, that's about 3. It's like 2.8 something or whatever. That's a different number. If you put E, you'll get a different number. So use the EE button, at least in Texas Instruments. I don't know what it is for other types of calculators. Okay. So all right. So recap with this problem, we have 2.45 moles of copper. How many copper atoms? We multiply by Avogadro's number, throw it in our calculators, get the number of copper atoms. In this case, 2.45 moles is equal to 1.47 times 10 to the 24 copper atoms. Anybody have any questions with this one? Okay, so let's see if you can figure this out. How many oxygen atoms in a half a mole of O2? So I'm also testing this. It's a tricky one. And this is just to have you think about moles. How many think we have A, half a mole? How many think B, 1 mole? How many think C, a quarter mole? D, 2 moles? Okay, so most people not playing, all over the board. O2, so what does this number mean on the bottom? So this means the bottom of the subscript means 2 oxygen atoms. So, and I'm just putting OX because my O looks just like my 0. So when you see a subscript like H2O, the 2 under the H means there's 2 atoms of hydrogen, and if it's not listed, it's 1 atom of oxygen. So something like glucose. So glucose there means that there's 6 carbons, 12 hydrogens, and 6 oxygens. That's what the subscripts mean. So if you have half a mole of O2, that means then you actually have twice as much oxygen as what's there. So then how many O atoms in that is 1. It's like if I have half a dozen people, how many hands do they have? And I know people don't necessarily have to have 2 hands, but most do. So if I have half a dozen people, how many hands do I have? I have twice as much. So I have a dozen hands. So does that make sense? Okay. Okay, you can do it the other way. Calculate the amount of carbon in that mass of pencil. So pencil lead is actually carbon, not lead. So when you do these problems, you also have to attack the problem. You have to look and say, okay, what's the given information? Where do I need to go with this? Our given information here is that we have carbon, and then we have a certain mass. So, and we want to know the number of moles, and we're given a mass of an element. And from this, then you can think, oh, I remember talking about the periodic table. And carbon has the bottom number in carbon. It's 12.01. That's the mass number. Or not the mass. That's the atomic, whatever, the terrestrial average, the atomic mass. So that's the amount that's here on Earth. Assuming this is carbon from the Earth, which is a pretty safe guess, right? We're not talking about Martian pencils yet. So carbon in moles, so we're going to do a dimensional analysis, 0.0265 grams of carbon, and we're looking for mole of carbon, and then we have 12.01 grams of carbon. And then just put that in our handy dandy calculators. And what does my handy dandy calculator say? Okay, 0.0265 divided by 12.01. And then this is 0.00221 moles of carbon. Does anybody want me to put the result of the calculator up there? Raise your hand if you want that. Okay. Because I can take a picture of it, but this one's pretty straightforward. And we can do multiples with this as well. So the next example, how many copper atoms in a copper penny with a mass of 3.1 grams? So here, 3.10 grams of copper. And then how are we going to do this? Well, we convert to moles of copper first, and then to copper atoms. The nice thing about chemistry class is that if you think, okay, I see a mass, how many moles is that? That's a pretty safe assumption you can do in this class. It's like, oh, I see a mass, what's the moles? So 3.1 grams of copper. So moles of copper, is it 63.55? I forget, we just did this. 63.55, okay, my short-term memory is still working. And then the moles of copper was, so 6.02 times 10 to the 23rd. Cu atoms, so everyone say Cu. Again, just like the number of days in a year, we're multiplying by 1. A mole of copper is, in fact, 63.55 grams of copper. 6.02 times 10 to the 23rd copper atoms is, in fact, a mole of copper. So units cancel. And then we are left with, I think I've already done this one. So here, I normally would go through and do this in class, but I couldn't figure out how to delete these whatever pictures. So I just covered them with white electronic ink. So that's what it looks like in your calculator if you put that in there. So this equals, if you want to answer, 2.94 times 10 to the 24th copper atoms. Okay, again here we're doing recap with this one. We are doing dimensional analysis. So attack the problem. What's the information that's given? We're given a mass of copper. And what does the mass of copper tell us? Well, tell us the identity of the material. It's copper. Tells the mass. And from that, what are the number of atoms? So we have to think, what's the missing step here? We're missing something. Like, okay, we got to calculate moles. So how do we calculate moles? Like, oh yeah, periodic table. Periodic table, and the molecular weight, molecular mass, or atomic, I should say, atomic weight, atomic mass of copper is written right there in the periodic table. So to get the periodic table, or if not, you have it memorized. You don't have to memorize the periodic table. You always have one in front of you. 63.55 grams per mole. So put that in the middle, and then by dimensional analysis, we can figure it out. And there's about 3 times 10 to the 24 copper atoms. So does that make sense? Anybody have any questions with this? Some people look confused. Think about it. And another item. So I've been teaching, this is my 13th year teaching at the University of Hawaii. And you start to see common mistakes that people make. And one of the most common mistakes I see is order of operations. So order of operations, and I mean, you probably noticed that my calculator's on my smartphone. This is a smartphone. It's not an AI. It's not it doesn't have artificial intelligence. We don't have any AI that can do chemistry yet. So right now, chemistry is a purely human endeavor. I mean, there's lots of apps. I got tons of chemistry apps. But the ability to solve chemistry problems, unless someone has done the exact problem and posted it somewhere like on Yahoo Answers, a computer, Google could not figure out how to do this problem. It probably could because it's somewhere in Pearson. Let's say I tweaked it and said, like, okay, how about 5 grams? So if Google could figure this out, it's because someone wrote 3.1 grams. I said, how about 5 grams of copper? Google couldn't figure it out. So a human could, though. Humans can do it. So, and if you notice some things that we're getting better, computers are not so good at figuring out like what if you skew numbers or something like that. they can't figure out that if you take a 3 and you turn it by 20 degrees, it's still a 3. Humans can do that, right? Or shrink it a little bit and then do something else. So eventually computers will figure out how to do that, and then maybe real authentication will happen by giving someone a chemistry problem. Who knows? So be a good day for me, I guess. But AI is getting smarter, but not as smart as humans yet. And our tools are smart, but they rely on human input. And we'll go more into order of operations later. I know we're about out of time here. So parentheses first, exponents and logs second, multiplication, division third, and then addition, subtraction, and it goes left to right. And I know when it comes to some problems and some common mistakes, we'll talk about that. Last question here, how many oxygen atoms are there in 12 grams of oxygen gas, O2 gas? So I know we just finished class there. So I will just go ahead and tell you the answer. It is close to 1 mole. So 16 grams of oxygen is exactly 1 mole of oxygen. So even though that means that we have Avogadro's number. So, all right. This class is then over, and I will see. Oh, Monday's a holiday. So I'll see you a week from today. So, all right. So see you later. Come up if you have any questions. Oh, and if you have time, there's some events going on. I know in the student lounge in the middle of the great campus lawn.
Do you know what it is?
I know you can get a flu shot. And that's what I'm going to get.
I really don't know if I want shots today.
I
get it though. People are.
I'm a teacher. I need it.
I understand. Well, all the adults are like even toddlers now.